Usually a medical diagnosis implies this certain baseline of, like, precision.
Right, yeah, like it resembles engineering in a way.
Exactly. I mean, if you break your arm, the x-ray reveals this jagged white line on a black background, and the doctor simply points to it and says, well, there it is.
Broken or not broken, it's a clean binary state.
Yeah, and we find comfort in that visibility, right? But then you step into the world of artificial intelligence, and it's like that x-ray just shatters.
Oh, completely.
We are suddenly looking at a technological landscape where visibility is practically non-existent. Like, we don't genuinely know how it thinks.
We struggle to even define how it works.
Right. And there is this massive disagreement on what it fundamentally even is. So today, for this deep dive, we are bypassing the dense computer science jargon.
Thank goodness for that.
Yeah, we're going to decode the true fundamental nature of artificial intelligence using a single, profound academic parable.
Which is honestly a highly effective approach.
Yeah.
Because, the discourse around AI typically falls into two really unhelpful extremes.
Yeah, totally.
It is either buried in impenetrable mathematics and computer science terminology, or
it floats away into, like, philosophical science fiction, right?
exactly, finding a grounded mechanical framework to understand how large language models actually navigate human information is just really rare.
Well, we have exactly that framework today. We're exploring a brilliant essay. It's titled The Mathematician's Flame by William L. Weaver.
Oh, it's such a good piece.
It really is. It was published on his Substack, Independent Variables. And Weaver brings 30 years of STEM experience to this analysis.
30 years. I mean, when someone spends 3 decades working across science, technology, engineering, and mathematics, their perspective carries immense weight.
Yeah, especially on how those distinct disciplines approach problem solving.
Right, and he uses this classic academic joke to illustrate the architecture of modern AI.
It's so clever. And the specific details of this story are going to serve as the blueprint for our entire discussion today.
The precision of the narrative is really what makes it useful. It is not just a punchline, it is a structural lens.
Right. It allows us to isolate how different analytical minds process novel information.
Which in turn reveals exactly how a neural network processes language.
Okay, so let's unpack this. Let's set up the laboratory. I want to lay out the literal progression of this parable exactly as Weaver presents it.
Let's do it.
So we're starting with the professor establishing a baseline. As the story goes, the professor called 3 of his students into the laboratory.
Okay.
An engineering major, a physics major, and a mathematics major. And he says, this is today's lesson. Observe.
Setting the stage.
Right. So in the center of the room, a metal waste can full of shredded paper sat on the floor. And next to it stood a table holding a full pitcher of water.
Got the picture.
So wordlessly, the professor lights a match, tosses it into the waste can, and watches as the paper ignites.
Just starts a fire in the lab.
Casually starts a fire. He then picks up the pitcher, pours the water over the flames, and extinguishes the fire. Then he clears the lab and instructs the students to enter one at a time for their exam.
So, before we examine the students, we really have to isolate the professor's action here.
Yeah.
He is establishing a scientific control.
A baseline reality.
Exactly. In any empirical discipline, you must define the parameters of reality before you introduce a variable.
Right.
The professor has demonstrated a known problem state, a fire contained in a waste can situated on the floor.
Yep.
And he has demonstrated a known, validated solution state, pouring a pitcher of water over it to eliminate the fire.
So he is literally giving them the answer key before the test begins.
Well, he is giving them a localized answer key. He is providing a proven protocol for one highly specific environmental state.
Oh, I see.
The true test is not whether they can memorize the protocol. The test is observing how their specific academic disciplines dictate their behavior when the baseline parameters inevitably shift.
And shift they do, which brings us to the first variable. So picture yourself in this room, right? After resetting the scene, the professor called the engineer inside. The engineer observed that the setup had changed.
Here we go.
The waste can full of shredded paper had been moved onto the table right next to the pitcher of water.
Okay, so a spatial shift.
Exactly. The professor lights a match and sets the paper ablaze. And the engineer stands perfectly still.
Just watches it.
Just watches intently as the paper burns to ash and the fire naturally dies out for lack of fuel.
Wow.
Yeah. And when asked why he didn't act, the engineer replied, quote, I noted that this situation was completely different from the lesson. I did not have a certified method or tested standard operating procedure to deal with this novel setup, so I took no unverified action.
That is just brilliant. Weaver defines this response as the engineer's pragmatic governance.
Pragmatic governance, I like that.
On the surface, I mean, the narrative frames this as absurdity.
Like, dude, just put the fire out.
Exactly. The can moved a few feet vertically, and the students simply allowed a fire to burn in a laboratory. But underneath the humor, this perfectly encapsulates the governing philosophy of structural engineering and systems design.
Because engineering demands rigorous adherence to known operational parameters.
Yes. Meticulously mapped failure modes, standardized protocols. It is entirely focused on liability and containment.
You know, it's funny. We shouldn't mock their engineer here.
No, not at all.
Because if I am sitting on a commercial flight at cruising altitude, right, and some completely novel sensor warning illuminates on the dashboard, I want the pilot acting exactly like this engineer.
Oh, 100%.
Like, please consult the manual. Rely on tested standard operating procedures. I do not want some unverified, unmodeled intervention taking place while I am 30,000 feet in the sky.
And that right there is the core of pragmatic governance. To an engineer, an untested system state is a profound liability.
Right.
When a scenario lacks a validated procedure, allowing the system to run its natural trajectory within controlled boundaries is mathematically safer than risking an improvised intervention.
Okay, wait, let me process that. So the engineer in the parable observed the containment vessel, the metal can.
Yes.
They calculated that the fuel source was finite.
Exactly.
And they deduced that the fire would inevitably exhaust itself without breaching containment.
Yes. So doing nothing was an active decision based on a lack of protocol.
That makes so much sense because an unmodeled intervention, like, say, attempting to pour water at an unfamiliar height.
Right, you could knock it over.
Exactly. You could knock the burning can onto a flammable surface, and that introduces a chaotic variable.
The engineer stays within the boundaries of the known. They govern pragmatically. They require a manual written by human experience to navigate the world safely.
Wow. Okay, so if the engineer is, like, paralyzed by the absence of a manual, the next student represents a completely different operating system for reality.
A total shift.
So the professor resets the room and calls in the physicist.
Right.
Again, the waste can sat on the table next to the pitcher. The professor lights the match, and flames erupt.
Okay, same setup.
Same setup. But without hesitation, the physicist grabs the pitcher, pours the water into the can on the table, and extinguishes the fire.
Just handled it.
Just handles it. And afterwards, she explains, quote, I recognize the objective of the lesson. Heat plus fuel plus oxygen equals fire, and water reduces the thermal energy below ignition point. The table's height was an irrelevant spatial coordinate. I acted on the underlying physical laws.
What's fascinating here is what Weaver categorizes as the physicist's first principles realism.
First principles realism.
Yes. The physicist's starting point is fundamentally opposed to the engineer's.
Because they don't care about the manual.
Exactly. Where the engineer seeks a protocol constructed by human experience, the physicist aggressively strips away environmental noise to uncover invariant natural laws.
So the table is literally just noise to the physicist.
Just noise.
Because it's an irrelevant spatial coordinate. The laws of thermodynamics operate independently of elevation within that room.
Right. The physical state dictates the action, entirely independent of the contextual framing.
How does this mindset differ from the engineer in a practical sense, though? Like, for the listener, what is the core difference?
Well, the physicist understands the causal mechanism of combustion. They understand the causal mechanism of thermal reduction via water. They don't need a standard operating procedure because they possess the fundamental source code of reality.
They understand the physics of it.
They have a causal understanding of the environment.
You know, I find this distinction crucial when we think about the history of artificial intelligence.
Oh, absolutely.
Because in the early days of computer science, researchers genuinely tried to build AI utilizing this exact first principles approach, right?
They did. They really did.
They tried to code systems that understood the physical and logical rules of the universe, like hoping the machine could deduce solutions based on laws.
You're referring to symbolic AI?
Right.
Or what they called good old-fashioned AI. Researchers spent decades attempting to write comprehensive ontological rulebooks for machines.
Trying to give computers a physicist's understanding of reality.
Exactly. Explicitly programming definitions like water puts out fire or a table is a flat surface.
But the problem is, The world contains way too much environmental noise for that to scale, right? Like you cannot write a manual for every possible contextual framing of a problem.
No, you really can't. The complexity of reality just immediately overwhelmed symbolic AI.
Because the physicist's approach works flawlessly in a controlled laboratory where variables can be isolated.
But human language and human interaction are endlessly chaotic. You can't program a first principles understanding of, say, sarcasm or cultural idioms or shifting context.
Yeah, there's no mathematical formula for a sarcastic eye roll.
Exactly.
Which brings us to the third student. And honestly, this is the theoretical foundation of modern computation. It's so good.
Grand finale.
So finally, the professor resets the room a third time and brings in the mathematician.
Okay.
The can sits on the table next to the water. The match is dropped. The fire rages.
Same novel problem.
Yeah.
The mathematician looks at the burning can, calmly picks it up, sets it down on the floor next to the table, and promptly walks out of the room.
It's so good.
I just love that.
And when the professor calls all three back into the lab and demands an explanation from the mathematician, she looks at him with quiet confidence and says, I reduced the situation to a previously solved problem and left the solution as an exercise for the reader.
That punchline perfectly encapsulates the mathematician's universal abstraction.
Universal abstraction. It is so arrogant. I love it.
Mathematics, in its purest theoretical form, is entirely detached from the messy physical labor of implementation.
It really is.
It is the art of mapping unfamiliar problem spaces into canonical, proven domains.
Okay, so let's dissect the mechanics of that mapping. The mathematician walked into a novel problem state, right?
Yes.
She did not have an engineering protocol for a fire on a table.
Nope.
She did not care about the underlying physics of thermal energy reduction.
Not at all.
But she possessed the initial baseline data of fire on the floor is a solved problem.
And that is all she needed. She applied a transformation function.
A transformation function.
Right. She physically altered the unsolved state, the fire on the table, into the exact geometric and spatial state of the solved problem, the fire on the floor.
Oh, wow.
And from a theoretical mathematical perspective, once that transformation is complete, the intellectual labor is finished. The problem is conceptually resolved.
Here's where it gets really interesting. It is the equivalent of locating the precise coordinates of buried treasure on a map and declaring yourself wealthy without ever picking up a shovel to unearth the gold.
Yes, exactly. The actual physical intervention, the sweeping, the pouring of water to extinguish the flame, is dismissed as a mere implementation detail.
An implementation detail? That's hilarious.
The mathematician proves that a path to resolution exists. They prove it by reducing the novel anomaly back to a known constant.
And this concept, right, this concept of state reduction is the pivot point for Weaver's entire thesis regarding artificial intelligence.
It absolutely is.
Because we have this massive, pervasive societal misconception that large language models act like the physicist or think like the engineer.
Which they don't.
Right. But when I interact with a sophisticated AI, it presents itself as an incredibly knowledgeable, rule-abiding entity. Like, it feels like I am conversing with a system governed by pragmatic rules and a deep understanding of reality.
But it's an illusion. It is an illusion created by the scaffolding.
Yeah.
We must cleanly separate the interface from the core architecture.
Okay, explain that.
Well, AI systems are undeniably built through monumental engineering efforts.
Sure.
We are dealing with optimized silicon architectures, massively distributed data networks, colossal GPU clusters requiring immense thermal regulation.
All the hardware stuff.
Right. And that hardware infrastructure is strictly governed by the engineer's pragmatic governance and bound by the physicist's first principles realism.
Okay, wait, I get that the hardware is bound by physics and engineering, but aren't we seeing modern AI models being trained with extensive behavioral protocols? Like constitutional AI, reinforcement learning from human feedback, massive trust and safety guardrails. Doesn't that make it an engineering system? It sounds like we are successfully forcing engineering governance directly onto the cognitive behavior of the machine.
We are forcing engineering governance onto the output of the machine, not the nature of the machine.
Okay, that's a huge distinction.
It is. Those safety guardrails are scaffolding. They are filters applied after or during the generation process to shape the interface. But if you strip away the silicon servers, the user interface, and the safety filters, the fundamental essence of the model itself is not an engineering system.
It's not.
It does not possess a moral framework, it does not follow a physical law, and it does not understand the causal nature of the world. At its absolute core, an artificial neural network is pure high-dimensional mathematics.
It is the mathematician moving the can to the floor.
Yes, it is an enormous high-dimensional vector space mapped by hundreds of billions of parameters, functioning exclusively as a mathematical reduction engine. It transforms novel inputs into previously solved problem spaces.
Okay, so if the model fundamentally lacks an understanding of reality and is completely detached from the physical properties of what it is
No, definitely not. Relying on whole words is computationally inefficient and linguistically fragile.
Why is that?
Because if the system only understood whole words, it would treat understand, understanding, and misunderstand as entirely separate, unrelated entities.
Oh, right. It wouldn't see the connection.
Exactly.
Oh,
Instead, models utilize subword tokenization. They fracture language morphologically.
right.
So a simple word like apple might be a single token. But a complex word like unbelievable is sliced into prefixes, roots, and suffixes.
So it slices it into unbelieve and able.
Precisely.
And this allows the system to recognize structural patterns across different words, right? Like it sees the untoken and mathematically correlates it with negation, regardless of what root word follows it.
Exactly. Punctuation marks, code fragments, even syllables in foreign languages are fractured into these discrete, standardized tokens. When you input a prompt into a large language model, it does not read a sentence. It ingests a sequence of fragmented atomic tokens.
Okay, so the raw prompt, the human language, is fragmented. What happens to these tokens then? How do they get into the math part?
This brings us to vector encoding and the concept of latent space.
The latent space.
Yes. So the system has to translate those fragments into the mathematical realm. Each token is mapped to a mathematical coordinate called an embedding vector.
Okay, help me visualize this. Imagine a giant 3D graph, right? Like longitude, latitude, and altitude.
Sure. X, Y, and Z axis.
Right, so you can easily plot a coordinate in a physical room. Is the AI doing that, but with like thousands of dimensions?
That is exactly what it's doing. A large language model performs this exact geometric mapping, but in a latent space consisting of thousands of dimensions, assigning a distinct geometric coordinate to every single token.
So the AI is assigning specific coordinates to our words, turning messy human language into a precise numeric sequence in this massive space.
Yes, and this high-dimensional topography is the core of the machine's intelligence.
How does it know where to put them, though?
During its initial training phase, the model ingested billions of documents. As it processed those texts, it constantly adjusted the mathematical coordinates of each token based on the context in which it appeared.
Okay.
This creates semantic clustering. Tokens that appear in similar contexts are physically moved closer together in this multi-dimensional space.
Oh, I see. So the system learns that the token for king and the token for queen frequently appear surrounded by similar contextual tokens, words like throne, rule, or monarch.
Exactly.
Therefore, it assigns some coordinates that are mathematically proximate in latent space. It doesn't know what a monarch is. It just knows their geometric distance is incredibly short.
It measures semantic distance as physical distance. The concept of king and queen are close, but the concept of king and, say, toasters are separated by vast mathematical distances because their contextual surroundings in the training data rarely overlap.
But wait, language changes based on context. Like the word bank has a completely different meaning if it is surrounded by the tokens river and water versus the tokens money and vault.
Which is where the attention mechanism of the transformer architecture becomes critical.
Okay, attention mechanism.
The embedding vector of a token is not entirely static. The attention mechanism analyzes all the surrounding tokens in your specific prompt and dynamically shifts the coordinate of the target word.
Oh, wow.
So it pulls the token for bank closer to the financial cluster or the geographical cluster based on the gravity of the words around it.
So it is calculating a highly specific mathematical state for my exact prompt.
And this is where the laboratory parable perfectly aligns with the technology.
Right.
When you hand that tokenized, dynamically vectorized prompt to the AI, you are presenting it with a completely novel, unfamiliar environment.
I am handing it a burning wastebasket on an unfamiliar table.
Exactly. The system is blind to the physical reality of your prompt. It does not attempt to construct a first principles understanding of the topic, like the physicist would.
It doesn't try to invent a theory of combustion.
No. Instead, it initiates a massive mathematical state reduction.
State reduction.
Yes. It calculates the complex geometric relationships and mathematical distances between the input vectors you provided and the billions of previously observed optimized token patterns it saw during training.
It compares my novel problem state against every solved problem state it has ever mapped.
It is seeking the mathematical equivalent of the fire on the floor.
Okay, but how does it get from measuring distances in a 5,000 dimensional graph to actually writing an essay? How does statistical probability transform those measurements into coherent, original human sentences?
It relies on probability mapping.
Probability mapping.
Right. So once it maps the geometric relationship of your input, it calculates the statistical probability what the very next output token should be based on the preceding sequence.
Just the next token.
Just the next one. It does not draft a complete essay in its mind. It predicts one single atomic unit of information.
So if I input the sequence the sky is, the model navigates to that specific cluster of coordinates in latent space, analyzes the trajectories of similar sequences in its training data, and concludes that mathematically the highest probability for the next vector is the token blue.
Yes. It then appends blue to your original context. The new sequence becomes the sky is blue, and
then what?
It recalculates the entire geometric state, calculates the statistical probability again, and selects the next token. It repeats this process iteratively.
So it's bringing back the mathematician's catchphrase. The AI transforms an unfamiliar problem state into a previously solved problem space. It reduces the situation to a previously solved problem.
Yes.
But wait. If we view the system strictly as a probability engine mapping vectors in latent space, it fundamentally redefines how we should interpret its failures, doesn't it?
Oh, absolutely.
Because when a large language model hallucinates a fake legal citation or invents a historical event, it isn't lying or malfunctioning in an engineering sense?
No, not at all. A hallucination is a perfectly sound mathematical traversal that simply fails to align with external physical reality.
Because it doesn't know physical reality.
Exactly. If the model finds a cluster in latent space where legal terminology, specific formatting, and certain names are highly correlated, it will confidently predict the next tokens based on that geometry.
So the math is flawless.
The math is flawless. The statistical probability is high. It just happens that the generated sequence does not map to a factual event in the real world.
Because it operates like the mathematician. It does not verify the thermal properties of the fire. It just finds a topological path to a known shape.
Right. Truth, to a language model, is not a factual absolute. Truth is merely a high probability vector sequence.
Wow. Truth is merely a high probability vector sequence. That is wild.
This is exactly why treating the model like the engineer is dangerous. If you expect pragmatic governance, you expect the system to halt when it lacks a factual manual. But a mathematical reduction engine never halts. It always calculates the next most probable vector based on the parameters it was given.
It just keeps reducing the situation to a solved mathematical equivalent. It is functionally identical to the mathematician moving the can to the floor and declaring the problem resolved.
Functionally, yes. But here we arrive at Weaver's critical insight. This is the crucial difference.
Okay, what is the core difference between human mathematical abstraction and generative AI autocomplete?
Think about the mathematician in the story.
She smuggles the can to the floor, smugly produces the problem, steps away, and leaves the actual physical labor as an exercise for the reader.
Right. She proves a path exists, but she leaves you holding the heavy pitcher of water.
Yeah, she doesn't actually put out the fire.
Generative AI completes the arc.
Oh, it completes the arc.
Yes. It does not merely prove that a resolution path exists within latent space. It executes the reduction and calculates the downstream steps with devastating speed.
Automated execution.
Exactly. It loops the token prediction process thousands of times per second. It evaluates vast, multidimensional probability distributions.
Right.
Adjusts for parameters like temperature, which dictates whether it selects the absolute highest probability token or explores slightly less probable, more creative vectors.
Oh, right, temperature.
And it generates the resolution instantly.
So AI turns the mathematician's theoretical reduction into automated execution. It takes the abstraction, maps it to historical precedents, and then actually finishes the exercise for us.
Yes. It performs the labor that the human mathematician refuses to do.
That is incredible.
Where the engineer requires a manual, and the physicist requires time to derive the mechanics, and the mathematician abandons the implementation. The AI seamlessly connects theoretical state reduction with automated execution.
You know, there is a brilliant just delightful self-referential detail in Weaver's post that perfectly illustrates this.
Oh, the Gemini thing.
Yes. In the attribution at the end of his essay, Weaver notes that he actually developed the article through an iterative conversation with Google Gemini 3.6 Flash Extended.
It's so ironic. He used a mathematical reduction engine to write an analytical essay explaining that AI is a mathematical reduction engine.
It is the ultimate demonstration of his thesis. I mean, he provided the novel prompt, the burning can on a table, and the AI rapidly calculated the token probabilities, mapped them to previous linguistic structures regarding physics and engineering, and automatically executed the essay.
It mapped his novel intellectual problem into the solved space of structural essay generation.
So, if we synthesize all of this, the baseline reality, the failure of pragmatic governance in fluid environments, the limitations of first principles realism in chaotic data, and the sheer power of universal abstraction.
Right.
How does this shift the listener's relationship with the technology today? Like, as we integrate AI into our daily workflows and research, what is the takeaway?
It demands a fundamental shift in user intent.
Okay.
If you interact with an LLM believing you are delegating tasks to an automated engineer, you will implicitly trust its outputs, assuming they are constrained by validated safety protocols and factual manuals.
And if you believe you're consulting an intuitive physicist, you will assume the model grasps the causal reality of your prompt.
Both of those assumptions lead to catastrophic user error.
Because the machine is blind to reality.
We are handing our problems to a mathematical reduction engine, and a reduction engine excels exclusively at finding where a problem has been geometrically solved before. But it can only navigate to the correct coordinate space if we provide precise initial vectors.
So the AI can map the latent space flawlessly, but we are the ones providing the initial coordinates through our prompts.
Yes. If we hand the machine ambiguous low-resolution context, it will beautifully and flawlessly execute a mathematical reduction into an irrelevant output.
So the machine performs the mathematics, but the human must provide the meaning. The responsibility for defining the reality of the situation remains entirely with us.
Exactly. We aren't delegating to an engineer or a physicist.
We have dissected a massive paradigm shift today. I want to thank you all for joining us on this deep dive.
It's been a great journey.
It really has. We moved from a physical laboratory with a burning wastebasket to the high-dimensional topography of latent space. We explored why engineering models fail in fluid contexts, why first principles physics cannot map chaotic human language, and why universal mathematical abstraction serves as the engine of modern artificial intelligence. We broke down subword tokenization, geometric clustering, attention mechanisms, and statistical probability mapping.
We separated the physical shell of the hardware from the mathematical soul of the architecture.
Exactly. So I'll leave you with a final lingering thought to mull over, straight from Weaver's observations. Weaver noted that AI can solve the problem, provided we know how to ask the right questions when the room catches fire. If artificial intelligence is the ultimate mathematical reduction engine, executing solutions based purely on the parameters of our prompts, are we spending enough time learning how to define the problem? Or are we too busy staring at the fire?
That is the question, isn't it?
Think about that the next time you open a prompt window. Keep asking questions, keep exploring the architecture of the tools you use, and we will catch you next time.